Imagine a star so massive that it dwarfs our sun, burning at temperatures hotter than anything we can fathom. For millions, even billions of years, it dominates its corner of the universe, fusing elements in a fiery crucible, creating the very atoms that make up planets, moons, and even us. But nothing lasts forever, not even the mighty stars. And when their time comes, their deaths are nothing short of spectacular. Some stars collapse into dense, smoldering embers, while others go out with a cosmic bang, unleashing explosions so powerful they outshine entire galaxies. But where do they go after they die? Do they truly disappear, or do they leave behind echoes, haunting reminders of their once glorious existence? This is one of the universe's greatest mysteries, the fate of stars after their final breath. And today we're venturing into the cosmic graveyards where these celestial giants rest. But before we do, every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The life and death of a star are dictated by one simple yet powerful force: gravity. From the moment a star is born, it exists in a delicate tug-of-war. On one side, gravity is constantly pulling inward, trying to crush the star under its own weight. On the other, nuclear fusion, an unstoppable energy source, pushes outward, counteracting the force of gravity. As long as there's fuel to burn, the star survives. But the moment that fuel runs out, the balance is lost and everything changes. So, what happens next? That depends on the size of the star. Let's start with small and medium-sized stars, the ones similar to our Sun. These stars don't die in violent explosions. Instead, they undergo a slow, almost poetic demise. Over billions of years, they expand into red giants, growing so large that they can swallow entire planets. If our Sun followed this path, it would someday engulf Mercury, Venus, and even Earth. But despite their terrifying size, red giants are fragile. Their outer layers gradually drift away into space, creating breathtaking clouds of gas and dust called planetary nebulae, celestial grave markers glowing in the darkness. What's left behind is a white dwarf, a tiny, incredibly dense core. No larger than Earth, but with the mass of the Sun. Imagine compressing a car down to the size of a grain of sand. That's how dense a white dwarf is. These stellar remnants no longer generate energy. They simply radiate leftover heat, slowly fading over trillions of years. Eventually, they'll become black dwarfs, cold, dark remnants of dead stars. But here's a twist. Black dwarfs don't actually exist yet. The universe is only 13.8 billion years old, and white dwarfs take far longer to cool. That means no black dwarfs have formed yet. We are witnessing a phase of the universe where these objects are still in the making. But not all stars go quietly. When a star much larger than our Sun reaches the end of its life, it faces a far more dramatic fate. These stars don't just collapse, they explode. This event, known as a supernova, is one of the most powerful forces in the universe. A single supernova can release more energy in a few seconds than our Sun will produce in its entire lifetime. Imagine watching a star suddenly blaze with such intensity that it outshines an entire galaxy. That's the sheer power of a supernova. But why do these explosions happen? The answer lies in the very heart of the star. Throughout its life, a massive star fuses lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen, and so on, building up a layered core like an onion. But when the star reaches iron, everything stops. Unlike other elements, iron cannot be fused to produce energy. It's a dead end. With no outward force to counteract gravity, the core collapses in an instant. The outer layers crash inward, rebounding violently, and in a fraction of a second, a colossal explosion rips through space. Supernovae don't just destroy, they create. The elements forged in these explosions, gold, silver, uranium, scatter across the cosmos, seeding new planets and future stars. In fact, much of the calcium in your bones and the iron in your blood was once part of a long-dead star. We are quite literally made of stardust. But what happens next? The aftermath of a supernova depends on how massive the star was before it died. If it was large but not overwhelmingly so, it leaves behind an incredibly dense core, a neutron star. These objects are so compact that a single teaspoon of neutron star material would weigh as much as Mount Everest. Some of them even become pulsars, spinning neutron stars that emit beams of radiation, flashing like cosmic lighthouses in the darkness. And then there are the real monsters. If a star is massive enough, its core collapses beyond the point of no return. Gravity takes over completely, and a black hole is born, a region in space where the gravitational pull is so immense that not even light can escape. A black hole doesn't have a surface. Instead, it's a one-way door in space-time. Anything that crosses the event horizon, the invisible boundary around the black hole, is lost forever. But the story doesn't end there. Some black holes continue to grow, feeding on gas, dust, and even entire stars. Over time, they can become supermassive black holes, lurking at the hearts of galaxies, shaping the very structure of the universe itself. In fact, our own Milky Way has a supermassive black hole at its core, a silent giant known as Sagittarius A star. How did it get there? And what role do these cosmic behemoths play in the grand design of the universe? In the next section, we'll journey deeper into these celestial graveyards, exploring the formation of neutron stars and pulsars, uncovering the mysteries of black holes, and discovering the strange, mind-bending effects they have on time and space. Stay with us as we unravel the secrets of the universe's most enigmatic remnants. Imagine you're standing at the edge of an abyss, staring into absolute darkness. You drop a stone, expecting to hear it hit the ground, but there's nothing. No sound, no end, just an infinite silent void swallowing everything in its path. This is what happens when a dying star collapses past the point of no return, when its gravity becomes so powerful that space itself folds inward, and time stretches into eternity. This is a black hole. But before we fall too deep into this cosmic enigma, let's take a step back. Not every star becomes a black hole. Some leave behind something equally bizarre: neutron stars, the universe's ultimate paradox. Unimaginably tiny, yet impossibly heavy. When a massive star dies in a supernova explosion, its outer layers are ejected into space, but the core, what's left of the star's heart, does something extraordinary. Instead of disappearing, it collapses into a ball of neutrons, squeezed together so tightly that the entire mass of the star is packed into a sphere no wider than a city. Let's put that into perspective. Imagine taking the sun, an object over 800,000 miles wide, and compressing it down to the size of Manhattan. The gravity in this tiny remnant is so strong that atoms themselves are crushed, their electrons and protons merging to form neutrons. That's why they're called neutron stars, matter so dense that just a single sugar cube of it would weigh as much as Mount Everest. And they don't just sit still. Many neutron stars spin at mind-boggling speeds, some rotating hundreds of times per second. And then there are the pulsars. Pulsars are a special type of neutron star, but they don't just spin, they flash. As they rotate, they shoot out beams of radiation like cosmic lighthouses sweeping across the universe. Some pulse with such precision that they rival atomic clocks, ticking down the passage of time across the cosmos. In fact, when pulsars were first discovered in the 1960s, scientists briefly wondered if they were signals from an alien civilization. So regular were their pulses that they seemed artificial. But no, these were not messages from extraterrestrials. They were the heartbeats of dead stars, still beating long after their deaths. But what happens when a star is even larger, when its mass is so great that not even the formation of a neutron star can stop the collapse? That's when we get something truly terrifying: a black hole. A black hole is not a physical object in the traditional sense. There's no surface, no solid core, just an invisible, bottomless pit of gravity. Once something crosses its event horizon, the point beyond which nothing can escape, it's gone, forever. Not even light, the fastest thing in the universe, can break free. That's why black holes are black. They devour all light, all matter, all energy with no trace left behind. But here's where things get strange. Time itself behaves differently near a black hole. If you were to watch an object falling toward one, you would see it slow down, its movement stretching out as if caught in an endless loop. To the outside observer, it would take an eternity for that object to actually fall in. But from the perspective of the falling object, everything would seem normal, until in an instant it's gone. And what about someone who dares to cross the event horizon? Theoretically, they would experience what physicists call spaghettification, a process as bizarre as its name suggests. Because black holes exert extreme gravitational forces, they don't pull on an object evenly. The part of you closer to the black hole would be stretched out, while the part farther away would lag behind. In other words, you'd be stretched into a long, thin strand, like a piece of spaghetti, until you were eventually torn apart, atom by atom. A gruesome fate, yet one that remains purely theoretical, because no one has ever returned from a black hole to tell the tale. But the story doesn't end with destruction. Black holes are not just cosmic vacuum cleaners, endlessly consuming matter. Some of them, especially the supermassive black holes at the centers of galaxies, are engines of creation. When gas and dust spiral into a black hole, they don't always disappear right away. Instead, they form an accretion disk, a swirling, fiery halo of material heating up to millions of degrees, emitting powerful jets of energy. These jets shoot out at nearly the speed of light, shaping galaxies, triggering star formation, and even influencing the fabric of the universe itself. At the heart of our own Milky Way, 4 million times the mass of the Sun, lurks Sagittarius, a star, a supermassive black hole hidden behind thick clouds of gas and dust. We've never seen it directly, but we've observed its influence. Stars near its core move at incredible speeds, their orbits distorted by an unseen force. And in 2019, for the first time ever, scientists captured an image of a black hole's event horizon, an eerie glowing ring of light surrounding pure darkness, a silent maw consuming everything in its path. But black holes raise more questions than answers. What happens inside them? Do they lead to another universe? Could they hold the key to time travel? And what about Hawking radiation, the groundbreaking theory that suggests black holes might not be eternal after all? Some physicists believe that, over unimaginable timescales, black holes slowly evaporate, disappearing in a burst of energy. If true, then even these cosmic giants are not immortal. But if black holes fade, where does all the information go? The universe has strict rules. It doesn't like to lose information. The laws of physics state that every particle, every bit of data, must be preserved in some form. So what happens to the matter swallowed by a black hole? Does it simply cease to exist? Or is it somehow encoded in the event horizon, waiting to be released at the end of time? This is the black hole information paradox, a puzzle that has baffled physicists for decades. If we could solve it, we might uncover new laws of physics, ones that could change our understanding of space, time, and reality itself. Black holes are not just the remains of dead stars. They are the most mysterious objects in existence, bending the very fabric of reality. But they are not the only remnants left behind in the vast graveyards of the cosmos. There are stranger things still, hypothetical objects even more extreme than black holes. Could there be quark stars, composed entirely of subatomic particles, or gravitar stars, bizarre alternatives to black holes that defy conventional physics? And what about wormholes? Are they real or just science fiction? In the next section, we venture beyond the known into the uncharted territories of theoretical physics, where the line between reality and speculation begins to blur. Stay with us as we explore the strangest, most mind-bending possibilities lurking in the depths of space. Picture this. You're floating in space, surrounded by a sea of stars. Suddenly, ahead of you, a shimmering doorway appears, a rift in the very fabric of the universe. It's not a black hole, not a void of destruction, but something else, something stranger. A tunnel, a bridge, a gateway to an entirely different part of the cosmos. Could such a thing exist? Could black holes be more than just cosmic graves? Could they also be portals? For centuries, humanity has peered into the abyss, searching for answers. And as we've uncovered the secrets of dying stars, we've stumbled upon theories that push the boundaries of reality. Among them, one idea stands out, a possibility so profound that it could rewrite everything we know about space and time. The wormhole. A wormhole, in theory, is a shortcut through space-time. Instead of traveling light years across the galaxy, a wormhole could allow you to step in at one point and emerge instantly at another, like a secret tunnel cutting through reality. The equations of general relativity, the very same equations that predict black holes, suggest that wormholes could exist. But are they real or just mathematical fantasies? To answer that, let's go back to where this idea began. In 1935, Albert Einstein and physicist Nathan Rosen proposed something called an Einstein-Rosen bridge, a hypothetical connection between 2 points in spacetime. At first, it seemed purely theoretical, but decades later, scientists began wondering, could black holes be the entrances to such bridges? Could something, perhaps even someone, fall into a black hole and come out somewhere else in the universe? Or in another universe entirely? Here's the problem. Wormholes, if they exist, wouldn't be stable. The intense gravitational forces would crush them instantly, snapping them shut before anything could pass through. But what if there was a way to hold them open? Some scientists believe that a special kind of exotic matter with negative energy could stabilize a wormhole, keeping the tunnel open long enough for travel. Sounds like science fiction, right? And yet some of the brightest minds in physics, from Kip Thorne to Stephen Hawking, have seriously considered the possibility. But let's take this even further. If wormholes are real, could they allow for something even more incredible? Time travel. Here's how it could work. If one end of a wormhole moved at near light speeds, time dilation would cause time to pass differently at each entrance. That means stepping into one end might bring you out at a different point in time, not just in space, but in the past or future. Could this be the key to unlocking time travel? And if so, where are the time travelers? If the universe allows such things, wouldn't we have met someone from the future by now? But let's bring our focus back to reality, at least as far as we understand it. While wormholes remain hypothetical, there are real objects that may be even stranger. One possibility: quark stars, objects denser than neutron stars, but not quite black holes. These exotic stars, if they exist, are made entirely of quarks, the building blocks of protons and neutrons. Imagine a star where atoms themselves have collapsed, leaving only pure quark matter behind, a state of matter unlike anything else in the universe. And then there's an even more radical idea: graver stars. Some physicists believe that instead of forming black holes, some collapsing stars could create something different, an object with an ultra-dense exotic core that mimics a black hole but without an actual singularity. If true, it would mean black holes as we know them don't actually exist, only they're near-identical imposters. Could this solve the black hole information paradox, explaining what happens to matter that falls in? If black holes aren't true, singularities, could they somehow store or even release information back into the universe? And speaking of paradoxes, let's return to something we briefly mentioned: Hawking radiation. In 1974, Stephen Hawking made a shocking prediction. Black holes aren't entirely black. According to quantum mechanics, black holes should slowly emit a faint stream of radiation over eons. If true, this means black holes aren't eternal. Over time, they will evaporate, shrinking and eventually disappearing in a final burst of energy. But this raises another disturbing question. Where does all the information that fell inside go? In classical physics, information cannot be destroyed. Every particle, every event, leaves an imprint on reality. But if a black hole vanishes, does its history vanish with it? Does the universe simply erase whatever was lost inside? This is the black hole information paradox, a puzzle that has haunted physicists for decades. If we can solve it, we may unlock a deeper understanding of quantum gravity, the key to merging Einstein's theory of relativity with the strange, unpredictable world of quantum mechanics. But what if black holes don't just evaporate? What if instead of disappearing they explode? Some physicists propose that when a black hole reaches a certain small size, the buildup of quantum effects could cause it to detonate, releasing all the energy and information it had consumed in a final cataclysmic explosion. If this theory is correct, then black holes don't just die, they transform. And here's where things get even wilder. Some theories suggest that when a black hole collapses, it doesn't just disappear. Instead, it could give birth to an entirely new universe, an entire reality expanding within itself, hidden from our own. Could our universe in turn have been born from the death of another? If true, then every black hole might contain a universe within it, and our own cosmos might be the interior of someone else's black hole. This is the frontier of astrophysics, where speculation meets science, where imagination and mathematics collide. We stand on the edge of understanding, staring into the cosmic unknown, asking questions that may take centuries to answer. But one thing is clear: the deaths of stars are not the end. They are gateways to deeper mysteries, to new beginnings, to the very nature of existence itself. But before we conclude our journey, one final question remains. What happens to the last stars? When the universe grows old, when all the fuel is burned, when the last supernova has long since faded, what remains? In the next and final section, we venture into the endgame of the cosmos, the fate of the last stars, the ultimate darkness, and the final whisper of the universe. Stay with us as we unravel the ultimate destiny of everything. Imagine the night sky, the vast, seemingly infinite expanse of stars. As we look up, we feel the pull of the unknown, the beckoning allure of what's beyond our reach. But as the universe ages, that night sky we know so well will change. The stars will fade, and the cosmos will be left with the echoes of their once brilliant light. The time will come when all that's left is darkness, eternal, unyielding darkness. The Phaidai, last stars will burn out, the black holes will have evaporated, and the universe will be cold. We call this the heat death of the universe, a slow, inexorable process where everything reaches a state of maximum entropy. No more new stars will form. No more galaxies will collide and dance in the light of countless suns. Instead, the universe will continue expanding, its energy stretched thin across ever-increasing distances. The stars that remain will burn out one by one, their light slowly fading into the abyss, and after a time there will be nothing, just the faintest remnants of a once thriving cosmos. But what happens in those final moments? When the last star dies, when its fuel has been consumed, when it no longer has the power to resist the pull of gravity, what becomes of it? At the end of its life, the final stars won't be like the ones we know. They will be incredibly faint, tiny, and slow-burning. Unlike the hot, fiery beacons of light we're used to, these stars, known as white dwarfs, will continue to burn for billions of years, but eventually they too will run out of fuel. What remains behind will be cold, dark remnants of a once vibrant star drifting through space, a lonely ember of the past. Some may survive longer than others. Red dwarfs, the smallest and most numerous stars in the universe, will outlast the white dwarfs, burning their hydrogen fuel at an incredibly slow pace. These stars could continue to shine for trillions of years, far longer than our sun ever did. But even they have their limits. In the distant future, even the last red dwarf will fade, collapsing into a cold, dark cinder. As the stars die off, something strange will happen. The remaining remnants, white dwarfs, neutron stars, and black holes, will form a cosmic graveyard scattered across an ever-expanding universe. But even here, in this silent tomb, there's a beauty to be found. The gravitational pull of black holes will shape the remaining galaxies, slowly drawing them together. Over time, the last surviving objects will cluster together in dark, desolate regions of space. These final remnants will be isolated, slowly drifting away from each other as the universe expands further into oblivion. The black holes, those ultimate cosmic monsters, will remain for the longest time. As we discussed earlier, they don't just die. They slowly evaporate, emitting Hawking radiation, and as they lose mass, they shrink, slowly at first, almost imperceptibly, but over unimaginably long timescales. They will vanish, leaving behind nothing but the memory of their existence. The process could take trillions of years, perhaps even longer than the universe itself has existed. The end of the black hole era is a concept almost beyond comprehension, so far in the future that it is impossible for us to truly fathom. And yet, as the black holes dissolve, something even stranger might occur. The last burst of energy from a black hole's final moments could give rise to a new creation. This is the theory of the Big Rip, a scenario where the accelerating expansion of the universe tears everything apart, including black holes, atoms, and even space itself. At this point, the universe could enter a state where even the laws of physics break down, and the very fabric of reality unravels. But what about the ultimate fate of time itself? As the universe moves toward its final frozen state, time as we know it might lose its meaning. With no events to mark its passage, no stars, no interactions, time could grind to a halt, leaving only a deep, empty silence. It's a chilling thought, isn't it? Yet even in this dark, distant future, there are questions that linger, unresolved mysteries that we may never solve. What happens at the very end of the universe? Could there be a way to avoid the inevitable? Heat death? Is there another cycle waiting to begin? Some theories suggest that our universe could one day collapse in on itself in a big crunch, potentially giving way to a new Big Bang, a new cycle of creation. Others propose the idea of a big bounce, where the universe oscillates between expansion and contraction, forever creating and destroying itself. But we won't know. Not in our lifetimes, not in the lifetimes of our children or their children. And yet the questions remain. The search for answers continues. It's a journey that started with our understanding of how stars live and die. But the more we learn, the more we realize that death, as we understand it, may not be the end at. Also, what is the ultimate fate of the universe? Will it be a slow, quiet death, where even the echoes of the stars fade into nothingness? Or could something more remarkable, more profound, be waiting for us, hidden in the darkness of time itself? As we peer into the graveyards of dead stars, we're reminded of the fragility of existence. Everything in the universe has a beginning, a middle, and an end. But perhaps in the end, what we understand as end is merely the beginning of something entirely new. What if, in the cold, lifeless remnants of the universe, we will one day find the seeds for rebirth? Perhaps the cycle of life and death is not just a cosmic phenomenon, but a story as old as time itself. And so we must ask ourselves, what does this all mean for us? What is our place in the grand story of the universe? Will our story too fade into darkness, like the stars that came before us? Or will we find a way to leave our mark, to transcend time and space, and to reach beyond the final whispers of the universe? As we end this journey through the cosmic graveyards, take a moment to reflect on our place in this vast, unfathomable universe. The stars may die, black holes may evaporate, and galaxies may drift into the endless void. But the questions we ask, the mysteries we explore, and the curiosity we share with each other, that is what ensures the flame of discovery never truly dies. If you enjoyed this journey through the mysteries of the cosmos, leave us a comment and share your thoughts. What do you think the future of the universe holds, and what questions still keep you up at night? Share this video with friends who dare to look beyond the stars. Let's keep exploring this endless universe together.